When you buy a cluster of expensive AI accelerators, the prevailing narrative tells you to just scale faster. But what if that promise is failing because of how we engineer our workflows? The data suggests your hardware isn't broken. It's sitting in a state called execution idle, burning power while doing nothing. This video reveals why human workflow gaps are the true bottleneck behind AI's 10x potential and how to fix them without buying another chip. The story of modern AI infrastructure is often told as a procurement problem. Buy more GPUs, scale faster, get results. The data tells a different, more uncomfortable truth. We are witnessing a massive capital inefficiency where expensive hardware sits idle not because of supply shortages or broken silicon, but due to fundamental human workflow gaps and engineering misconfigurations. Consider the phenomenon known as execution idle. In this state, powerful accelerators remain allocated with programs loaded, yet visible compute activity drops near zero while they continue drawing substantial electricity across diverse workloads. Research shows that 19.7% of total execution time is spent in this high-power, low-activity state, consuming 10.7% of the cluster's total energy. In specific serving traces, up to 65% of energy use can be attributed entirely to these intervals, where no useful work happens. Scaling hardware without addressing workflow efficiency simply amplifies waste rather than output. The root cause is often a control-side bottleneck that engineers overlook when they prioritize GPUs over CPUs in static resource allocation. A pivotal study on multi-GPU LLM inference covering DGX H100 and B200 architectures demonstrates this clearly. When the CPU side becomes starved, critical tasks like tokenization, data I/O, inter-GPU synchronization, and kernel launches become choked points that stall the entire system. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. When CPUs are under-provisioned relative to GPU capacity, time to first token latency increases by 1.36x to 540x compared to adequately provisioned systems. Even advanced optimizations like CUDA Graphs fail to prevent these stalls if the control plane is overwhelmed. This means adding more GPUs without balancing CPU cores creates a choke point that renders additional accelerator capacity useless for inference workloads. You are not waiting on chips. You are waiting on yourself to stop treating GPU clusters like simple plug-and-play appliances and start designing for their specific nonlinear constraints. Even within single jobs, the inefficiency persists at the kernel level due to mismatches between our schedulers and how modern kernels actually execute. Research from ETH Zurich highlights that during memory-bound phases, such as decoding large models on A100s, compute units can sit dormant with utilization dropping below 10%, while other components like memory bandwidth saturate. Standard schedulers use temporal sharing to avoid interference, which causes long queuing delays and ignores the inherent inefficiency of single jobs running at less than 10% capacity during these specific phases. Existing spatial sharing tools lack the reliability to guarantee performance when collocating these mixed workloads because they fail to align with the granular reality of how modern kernels execute. This leads us to a deeper conceptual gap in infrastructure design. Academic analysis argues that systems often fail because they prioritize technical boundaries over psychological and ethical ones, creating a disconnect between human needs and system design. When systems are not needs-aware, they fail to align with the actual workflow requirements of engineers. This creates trust issues and misaligned expectations where expensive compute is deployed, but yields no proportional productivity gains. The 10x promise of AI isn't limited by silicon. It's stalled by this gap, where our engineering processes fail to match the complexity of the systems we build. We are not waiting on chips. We are waiting on ourselves to stop treating GPU clusters like simple plug-and-play appliances and start designing for their specific nonlinear constraints. The shift in perspective is critical for your career as a practitioner. This moves the anxiety from asking, "Did I buy the wrong chip?" to asking if my engineering process is flawed. For developers and data engineers, this provides a diagnostic framework for when ROI on AI infrastructure drops off. It empowers senior engineers to diagnose performance issues that look like hardware failures but are actually architectural or workflow errors. The actionable insight here moves beyond buying more GPUs to specific engineering judgments you can make today. You must audit your CPU to GPU ratios, implement dynamic downscaling for idle periods, and design workflows that account for memory-bound versus compute-bound kernel phases rather than assuming linear scaling from theoretical max specs. The hardware is capable. Our schedulers and job designs are not aligned with the granular reality of how modern kernels execute. The core thesis remains: we aren't waiting on chips, we are waiting on ourselves to stop treating GPU clusters like simple plug-and-play appliances and start designing for their specific nonlinear constraints. Scaling hardware without addressing workflow efficiency simply amplifies waste rather than output. The 10x promise of AI isn't limited by silicon. It's stalled by a needs-aware gap where our engineering processes fail to match the complexity of the systems we build. Hardware is cheap compared to wasted time. Workflow design requires effort but yields higher ROI when executed correctly. You must audit your CPU ratios, check for idle states that burn energy without work, and align system design with actual workload profiles rather than theoretical max specs. The role of the AI engineer shifts from a hardware operator to a workflow architect who bridges the gap between theoretical silicon capability and practical execution reality. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.